Hello everyone. Today I'm going to talk about number theory. Let me write down first. Number theory. So these numbers basically are whole numbers. So I'm going to talk about natural numbers mainly. The set 1, 2, 3, 4, these sets. You see, these are the natural numbers. Let me tell you some stories that how natural numbers came. It's when in the prehistoric age, when humans that time they feel need of counting something there for their day-to-day life. For example, that time they had domestic animals, they want to count it, so they need some things. What they used to do that time, they just collect stones and put them together for each animal stone. So in that way, and after few years they started marking on wall like this to count that things. And after some years, the numbers they invented, like in this way, 1, 2, 3, 4. So you see, these numbers came naturally. So this set is called the natural number. Now look at these sets. These sets do not have any fractions. All are the whole numbers. So due to this set have some special type property that the rationals q and the real numbers that do not have. So that special property will make these sets different. When we gonna do addition, division, subtraction, or some kind of equation on this number theory, that time that special property will make the difference. So there are two special properties. First one is called well-ordered set. This set is well-ordered, and another one we have. So before starting the well-ordered, let me tell you that a set is called ordered. Before saying well-ordered, you must know what is ordered. A numbers or set is said to be ordered if the numbers of that set, we can arrange them in a line. We can give them in an order so that we can compare each elements to the other elements. In that way, if we able to do that, so if we able to do each element a position so that we can find out who is bigger than others, we can form a order for that number. So that set is called ordered set. And now this set is not only ordered, it will be wellly ordered, and so that property is well ordered, that n processes. So let me give the definition of well ordering set. Well ordered. Set S is said to be well ordered if any subset of S has a least element. Okay, and the example would be natural number. Okay, so let me explain what I just wrote. This says a set, I wrote a set S is said to be well ordered if any subset has a least element. That means has a minimum element, has a starting element. So if we have a starting element so that we can count from that starting point, then that set, we will call that set well ordered. For example, we have natural number here. the minimum element is 1, so we can start counting from the 1. 1 is our starting point, the minimum element. 1, 2, 3, 4, this way. So this is more logical. If you have any set, then what will, if we start counting, what will you do? We first find who is the minimum one, and if we once find the minimum one, we will go to the next element, and then next. In the way we can start counting, right? So this is well ordered. Now another thing, look at this. 0, 1, all the real numbers in between 0 and 1. Can you find a minimum element here? You can't, right? Because there is no minimum element. So this set is not well ordered. Now what we do, if we put a minimum element here like 0. No, if let me put -1. No, okay, 0 is fine. Okay, now if we say this set has 0 a minimum element and union 0, 1, still this is not well ordered. Why is so? See, I have written here that any subset of S has a least element. So if we take the subset 0, 1, then we cannot find a minimum element. Well ordered says that if you take any subset, any subset, and then we can have a starting element at that subset, so that we can count from there on. You cannot count from these subsets. So in that way, since any subset has a least element, that property is not satisfying here. So this is not a well ordered set, but this is a well ordered set. Okay. Now one more thing, this set is well ordered. For that we find a minimum element. So let me write down minimum element is 1. Now look what is happening here. We have found 1. We can form all the numbers of natural numbers by this 1 only. So this number can be treated as a generator. Like you see, you have 1. If you add 1, then you will get 2. If you again add 1, you will get 3. In that way we can have all the natural numbers. So what is happening here, this number is the base, and these all other numbers are, we are finding all these numbers by inducing over 1. So this can be called induced elements, induced members, right? Okay. So base element and other elements, by inducing we are forming other elements. So this is happening since this set is well ordered. Look, in the rationals and in real numbers, since there is no minimum element, if I give you half in the rationals, you cannot find all the elements just using half. You can't. So due to this well ordered, we have the induced property. With this induced property, we have a special type of property for these natural numbers. That is our second property, and that is called mathematical induction. So let me write down the definition for mathematical induction. Since these numbers are having a base element and all the other elements we are getting as the induced elements, so for that, for each n belongs to natural number, let P Pn be a statement about n. Okay, and suppose that number 1, P1 is true. Okay, number 2, for every k belongs to natural number, if Pk is true, then Pk plus 1 is true. So we have these two properties. Then what can we say? Then Pn is true for all n belongs to natural number. Okay, so we have written here. Let me explain what I have written down. For each n belongs to natural number, Pn be a statement. Any statement, Pn, you just think whatever comes in your mind, a statement involving n, anything what is coming in your head. That Pn, we want to check that Pn is true or false. So how will we check? This is a tool. In that way we can check Pn is true or false. What is the tool? The tool says if P1 is true, that means the base steps, the P1 is true, n equals to 1, if we put, then Pn is true. And the next step, it says for every k belongs to natural number, if we take any k is of course finite, any k, then if Pk is true, then Pk plus 1 is true. So that is the thing. This is the induce or induction steps. So we call them, since this is the base steps, we call it base step, and due to the induction this portion is coming, so we call these steps as induction step. Okay, and in the induction steps there is two portions. One is we are taking that, okay, let's give you a little example so that you can have a little bit idea. Pn, for example, Pn 2n is always even. Okay, n belongs to natural number. Number 2, Pn n square is always even. N belongs to natural number. Now look, for an idea, we have written Pn is, you can think of Pn as a 2n is always even. I am stating this, 2n is always even. So is it true or false? How will we check? We check 2 into 1, it is 2. 2 into 2, just putting n equals to 1, 2, 3, 4. What we are getting? 2, 4, 6, 8, 10, 12, 14, in this way. So in this way whatever we are getting is even. So we can say that yes, 2n is always even. But how many times I have to check? Because n is infinitely many numbers, n has infinitely many numbers. So we cannot check all the numbers. We need certain algorithms so that we can say that this is true for all numbers. How will we do? These things we'll do. Mathematical induction. First, this is the rule. This says if P1 is true, we have to check for the base steps. that now put 2 into 1, it is even, so the base step is true. And another one says, here we are making an algorithm. We are saying if the k step is true, then mathematical induction is using the k plus 1 step is true. Just one step ahead is true. Like this. We are making this, if pk is true, then these things happen. So we call these lines as hypothesis. Hypothesis. What hypothesis? Induction. Induction hypothesis. This portion. Now find out that here you have to remember that okay. Let me just give you a view. Let me just give you a vow. This mathematical induction is compared with a ladder, an infinite ladder. Let me write down the. Let me draw something so that you can have a clear visualization. Suppose this is our ladder. Okay. And now P1 is here, so P1 is true. What is P1? P1 is you are now in these steps. P1. So P1 is true, and Pn is what? You are in the nth step, nth position. So after some time, suppose you are here. It is kth position. Pk is true. You are in pk position. Now, if mathematical induction is true, the second term, what it says that if pk is true, that means if you are in kth positions, then mathematical induction says that the just next steps you can move to the next steps. If this is true, that means if you are in here, then you can move to the pk plus 1 positions. You can move to here. You don't have to think the upper steps. You just think by mathematical induction. Mathematical induction is allow you to move from kth steps to k plus 1 step, right? And in this way, when you will be in k plus 1 step, if you apply again mathematical induction, then you can move to the k plus 2 positions, right? So in that way you can move upsides. Now the things are coming. Since you can move to the upside step by steps, there is no element that you are bypassing. You are taking every element and going upsides, right? Now if I ask you to find from the upside, find or give me a natural numbers n or steps so that I can't reach to that numbers. You can't give me, because you can't. There is no such n exist. So we can say now that since this is increasing, this pk or this pn step is true for all numbers. So what is happening here? We are just checking for n many numbers. That means finitely many numbers. Mathematical induction, what is doing here? It's just putting k and to k plus 1. So in that way is shifting k to k plus 1, and we are getting finitely many numbers pn, which we can check for finitely many terms, that we can say them that pn is true for infinitely many numbers. We are able to say. There is another examples that you might be familiar with. When we were kids, we have bricks. We put bricks side by side, and then we push to the first brick, and then the second, third, fourth, every bricks is falling down. That things happens, right? So what happens in that cases? Suppose you have infinitely many bricks, right? Now we will think these things like a mathematical induction. You have P1 is true. So what is P1? P1 is the first brick is fallen down. So that is the P1. First brick is fallen. Then the first brick, when it's fallen down, it will force to the second bricks to be fallen down. Then P2 will be true. In that way, P3 will be true. Mathematical induction says that suppose Pk or the kth brick is fallen down, then induction guarantees you, or induction, from the induction you are able to say that the Pk plus 1 brick will be fallen down. So these things will happen. So what is happening? Since all the bricks are one by one, it is fallen down, eventually all the bricks you will cover up and you will go in this way. So you cannot find any such n or any such bricks so that that brick will not be fallen down. There is no such brick, no such n exist. Therefore, we can say that Pn is true for all n. Now, see, we are checking, or we can say only finitely many numbers that Pn is true, that brick is falling down. But using these results, using mathematical induction, we are saying that this number, this Pn is true for all n's. You have to remember the things. One thing I should tell you. Here, look, the sentence, look at the sentences I have written here. I have written for every k belongs to natural numbers. Every k belongs to natural number means if you take any k from natural number. So if you are taking any k, that k becomes a finite number. So with that finite numbers, Pk is true. That is saying. And in the last line, what we are saying, Pn is true for all n. For all n. That means what? There is no such n remaining. For that, we can't say Pn is true. So that is not going to happen. Now, here we have written every, we have written here all. So this is a plural term. All is a plural term. And every is a singular term. We are thinking individually each element. For each element k, Pk is true. If you write here for all k belongs to, do not write here all. Okay. See, if you write that, if you write here all, what it would become? Look, if I write here for all k belongs to natural number, if Pk is true, so it's becoming what? It's becoming so silly, right? We are saying that Pn statement is true for all k belongs to natural number. So there is nothing to prove. We cannot say. If you write for all k belongs to natural number, I will cut your number. You can't write. Because individually, whatever k you take, that k is finite. So Pk is true for any finite number you choose. Then, if this is true, finally we will say that Pn is true for all n belongs to natural number. Okay, so just show me, just let me show you by a problem so that you can have a good idea how to use this mathematical induction in solving problems. Okay. Number 3 is like 1 plus 2 plus 3 plus, okay, just write Pn. Pn, here Pn is this. if we add n many numbers, we get n into n plus 1 by 2. 4 Pn equals to, if we add square terms with n many numbers, you will get n into n plus 1 into 2n plus 1 by 6. Now this can be done, but I will prove by mathematical induction on this, because this is a little bit easy, so you can do it so easily. Let me solve this one. 4. What we will show for the base step is true. So what is here? The base step. That means we have to show the P1 is true. Now for P1, if we put n equals to 1, what will you get? 1 into 1 plus 1, 2 into 1 plus 1 by 6. This gives 1 equals to 1 square. So that is P1 is true, because we can check that this is actually the P1. Now make an hypothesis. What was our hypothesis? That portion. For we assume, we assume that so there is our hypothesis. We assume that Pk is true. We have to write for k belongs to natural number. Okay. Like the other one, we cannot say Pk is true for all k belongs to natural number. That would be wrong if you write here all. So Pk is true. What does this mean? This means 1 square, that is 1 square plus 2 square plus 3 square plus k square equals to this, k into k plus 1 into 2k plus 1 by 6. Now we're gonna show that k plus 1 is true. P of k plus 1. For that we will take k plus 1 square, this term. Now these portions we already have this sum. Let's write it. Okay. Now we add the k plus 1 square term. Okay. So we take the k plus 1 factor and make it 6. Will come in our denominator, and now we will get the k into 2k plus 1 plus 6 into k plus 1. Here we go. K plus 1 into, now if we factor these things, what we get? We get okay, just let me break it down. After that we will again put it 2k square plus k plus 6k, 7k plus 6, okay, by 6 equals to k plus 1 into 4 plus, we can break them, 4k plus 3k plus 6 6. Now see, these results is, if we take this k plus 1 as a n, so k plus 1 plus 1 into 2k plus k plus 1, right? This is true for k plus 1, that is p k plus 1 is true. We assumed that pk is true. Now we have calculated that pk plus 1 is true. So we can say by mathematical induction, we can say Pn is true for all n belongs to natural number, right? In that way we can check that Pn, a statement about n, is true for all or not. We have given a rule, a tool, the mathematical induction. How we will use that tool to solve a statement Pn is true or false. So this is, you can see, this is just a checking process. Pn is true for finitely many, whatever numbers, whatever finite numbers you choose, Pn will be true. How will we reach to the infinitely many numbers? How can we say that this is true for all infinitely many numbers? We have seen, we have checked these things, and in this way you can say that yes, this is true by mathematical induction. So I guess all the other examples you can easily solve, and in the exercise there are some problems. I'm pretty sure you can easily do that. Okay, so I guess you can solve all the problems in exercise. If you have any questions or anything related to mathematical inductions that you didn't understand, you can contact me, you can tell me. I will definitely tell you the answer.